So today what we're going to be looking at is measuring segments in a circle. And it's going to be one key overriding concept to every equation we set up today that you absolutely have to follow every time. And if you do so, you're probably going to find this to be really simple. Every segment we measure will start at the point of intersection. Whether that point of intersection is going to be inside the circle or outside the circle. Every measurement we take must be a segment that starts at the point of intersection. So I'm never really going to take like the chord as one of my measurements for the calculation. The whole chord will not be used. We always start at the point of intersection. And that we multiply the two segments along the same line. So in order to get, when we have two set chords intersecting inside a circle like this, the equation we get is the length of AE, okay, times EC equals BE times ED. Sorry. Okay. We multiply this times this equals this segment times that segment. That's our basic premise today. Always starting at the point of intersection. What a lot of people do is, since the point of intersection is E, we'll start at E. So we'll go EB times ED equals EA times EC. Because all our segments have to start at the point of intersection. That's probably the single most important concept we get from this as we're setting up these formulas today. This is our new rule for finding measurements of segments and chords as they intersect in circles. And setting it up is really easy. I mean, I could say this is 4, and this is 6, and this is 3, and this is X. And so we just plug in 4 times 6 equals 3 times X. So 24 is 3X divided by 3, and look, we get X equals 8. It's that simple. It's really not difficult stuff that we're doing today. But we have to make sure we get it set up correctly. The formulas generally don't tend to be that too tough. If the point of intersection is outside, the equation does not change. It's just we need to be a little bit extra careful. Because my point of intersection is now out here. So the measurements I'm going to put together are EC times, and not CA, but EA. All segments that we measure must begin at the point of intersection. That's going to equal EB times what other piece? ED. Notice that just CA never gets used. Just DB never gets used. Now, this can be a little trickier because sometimes they may say, okay, this is X, this is 6, this is 4, and this is, I don't know, let's say 5. And the natural inclination that we're going to have, because we're just going to look at it, glance at it, and try to throw things into a formula right away, is they're going to say 6 times X equals 5 times 4. But that's not correct, is it? Be systematic about this. Slow yourself down, be very systematic. X times what? How long is the whole thing? X plus 6, or 6 plus X. Equals 4 times what? The whole thing, which is 9. Or 4 plus 9 if you prefer. And that's going to give us something like x squared plus 6x equals 36. So x squared plus 6x minus 36 equals 0. Oh my goodness, how do we solve that? That's why we spend our time with quadratic formula and factoring and all that sort of thing. This particular one does not factor, I don't think. I don't think two numbers multiply give me negative 36 and they had to give me 6. See, 36 is 12 and 3, 18 and 2, 36 and 1, 9 and 4. I'm not going to get a 6 out of that. So how would I solve that? Quadratic formula. Negative 6 plus or minus the square root of 6 squared minus 4 times 1 times negative 36 over 2 times 1. It's negative 6 plus or minus the square root of, oh boy, 4 times 36. Okay, hold on. 36 plus 4 times 36, 180. And 180 divided by 5 is 30. Okay. So that's negative 6 plus or minus 6 root 5 over 2. Because I can simplify that. If I want to, I could factor a 2 out of the top there. So that's 3 plus or minus 3 root 5. And it's going to be the plus because the minus is going to give me a negative length, which wouldn't make any sense. So this length here is 3 plus 3 times the square root of 5. Exactly. Now, that's a really, really hard problem. That was a really, really easy problem. That's a really, really hard problem. Most of the problems we're going to deal with this section are going to be somewhere in between. But essentially, you've now seen everything you need to know for this section. Because every equation pretty much sets up the same way. Some of the equations give us nice whole number answers that work out very easily. Some of the equations give us quadratics, which either have to be factored or solved using the quadratic formula. But we still set them up the same way and solve them out. Some are going to be easier. Some are going to be harder. Here, again, error correction. I put this on the test or the quiz, and I'll bet that 50 to 60% of people would say 10 times 11 equals 14 times x. Why? Because those numbers are, boom, they're right in front of us. So, of course, we want to do that. But that's not correct. So we have to be very careful. It'd be 10 times what? 21 equals 14 times 14 plus x. Now, this one's actually a little easier. That's 210. And when I distribute here, it's 196 plus 14x. So I subtract the 196 from each side. There's no x squared this time. Much easier problem. 14 equals 14x. So x is 1. Obviously not drawn to scale. Okay? Well, we found the answer. X is 1. So obviously, again, some of these problems are going to be easier. Some are going to be harder. But if you set them up correctly, you fought half the battle. And in most cases, when you set them up correctly, you're not going to get anything that's that difficult to solve. Oh, we did back here. But this time, no. It's not a problem. It's a lot easier when the x is on the inside. We can also do this with tangent lines. Now, tangent lines get a little bit tricky. You can get the idea. And notice that when I create a tangent line here, okay, I have a secant, so AC times AD. Notice what I'm measuring, AC and AD. I'm not measuring CD. For the tangent, because we can consider that the point of intersection is the same point for both. Okay? That's what's going on with the tangent, is both these 2 points have come together. So we essentially, square that value. Okay? Notice the values are always the same though. So for a tangent, essentially what we're figuring is that these 2 points of intersection have merged to one. We've slid this point D around here. We grab point, no, not the point, not the line. Grab the point. No, just grab the point. Oh, you silly thing. Okay, never mind. But if you just grab that point and slide it around, it's like they've merged into one. So we still get 2 segments. We still get 2 measurements, but they're the same. AB squared. Ah, you are here. Okay. Where's it from? Okay. So tangent lines work the same way. It's just that instead of just, because we don't have 2 segments to multiply, we just multiply the 1 segment twice. We square it. It's really what it comes down to. This is one that works out like one of the more difficult ones again, but again, we can set it up and solve it. So what do we get? Someone set up the equation for me. Starting at the point of intersection, my first segment would be this one here, which is how long? X. Times what would be my second segment? We start 6 plus X, or X plus 6, equals 8 times 20. So X squared plus 6X equals 160. So X squared plus 6X minus 160 equals 0. Can that factor? Well, my product has to be negative 160 and my sum has to be 6. You want to tell me 2 numbers multiplied to give me negative 160 and they have to give me positive 6. Let's think about it. 160 would be 160 and 1, 80 and 2, 3 doesn't go in, 40 and 4, 5 is what, 32, 6 and 6, no, 6 doesn't go into 160, 8 does, 20 and 8, 10 and 16, any of those going to give me a 6? The 10 and 16 are, aren't they? Which one has to be the negative one, the 10 or the 16? The 10 does, because the sum has to be positive. This is going to be X minus 10, X plus 16 equals 0. That means X equals 10 or negative 16. Which of those answers makes no sense for the length of a segment? The negative 16 makes no sense. So we've got our solution. Now you see why we spent that time working on quadratics earlier and factoring, because we have to do that as part of the section. Most of our problems really don't make us do that. Most of our problems are just linear. But occasionally one of those sneaks in, and that's what we have to be prepared for. This looks a lot worse than it actually is going to be, but it's going to be interesting. It's more of an extension style, but again, we get the principle. Start here. First segment is clearly just X plus 8. How long is my next segment going to be all the way out there? 2X plus 10 equals what? x plus 5, and 2x plus 16. Now this looks like it's going to be all sorts of nasty, doesn't it? But I want you to watch really carefully and see what happens. We have to FOIL these. That gives me 2x squared plus 10x plus 16x plus 80 equals 2x squared plus 16x plus 10x plus 80. What do you notice? Exactly the same, aren't they? So we get 0 equals 0. What does that mean? That any value of x will work. It's kind of interesting when you get it. At the very least, when I set it up, I was hoping the x squareds would cancel out, and they do. But even more so, everything cancels out. So we get 0 equals 0. That means we can put any value of x in and get a valid solution. It's a little unusual. But again, like we say, it's like an extension problem. Let's set up a couple more just for fun. Again, these are just good practice problems. And they might give us nice answers, they might not. This is a tangent and a secant. And we'll say this is x over here. This is 8, and we'll call this 10. Okay? 8 and 10. So what am I going to multiply? 8 times what? 18 equals what? X squared. So it's 80 plus 64 is 144. Is x squared. How do we solve that? Square root of both sides, so x equals plus or minus 12. But again, the minus doesn't make any sense to me, so x is 12. They really aren't that bad as long as you can remember to set up properly, which means starting at the point of intersection. That's the key element today. Over and over again, start at the point of intersection. Do not just use the chord by itself. One more. I'll relax. But like, really? Yes, one more. Okay. I'm going to call this 2 and this 14. I'm going to say this is 6 and this is x. How are you going to set that one up? 2 times 14. No, no, no. Start at the point of intersection. We never use the whole chord, do we? 2 times 14 equals 6x. So that would be 28 is 6x divided by 6. Well, that one worked out to 14/3. Okay, I can live with it. So that's how these problems set up and solve. Always start where? Point of intersection when you're setting these up. It's really not bad when you do that. And you know what? If you get stuck in the quadratic portion of this, I mean, if you get stuck here and you're not sure what to do, but at least you got it set up correctly, guess what? You're probably going to get most of the points on the quiz, aren't you? So at least you've set it up correctly. So getting the right setup is really critical. All right. Hold on. Oh, no, I wanted a new tab. That's all I wanted. So if you look at the assignment. There we go. Geometry homework. Please note we still have our benchmark scheduled for Wednesday, which, by the way, we're all caught up with Mrs. Ramson's class, at least at that point. I think Mrs. Herder and Ms. B. Walter still a little bit ahead. So we'll just review this tomorrow. There's really not that much in this I-2. It's a congruent segments when they're equally distant, and it's this sort of thing. So we'll do a little review in tomorrow, and then benchmark on Wednesday and moving on from there. We start dealing with arcs. So let the fun continue. And do your homework. Folks, seriously, If you do not practice this stuff, you will struggle with it. Okay?
Why is your phone so dirty class again?